We all know it. Walked it every day. But none of them were like these. The world's most dangerous ways to school. Freezing, climbing, risking their lives, all for the chance of a better future. Spectacular and sometimes simply beautiful. The world's most dangerous ways to school.
In Zamboanga del Norte, many students living in remote mountainous areas face intense challenges just to have basic education. Because there are no proper roads or bridges, many of them have to walk for more than 2 hours every day. Others have to pass more dangerous routes such as steep slopes, slippery rocks, and exposed tree roots covered with moss. Children have to dangerously climb a cliff-like area, or as we call it pang-pang, just to go to school. These conditions became even worse during rainy weathers, making the path more slippery and increasing the chances of accidents. Going to school is not only exhausting, but also dangerous for many students. Despite the difficulties, they continue to push through every day in order to attend school and work towards a better future.
So in this part, I am here to present our proposed bridge construction approach and bridge model in Maribago, Zamboanga del Norte. So this project aims to provide a safe, reliable, and cost-efficient crossing solution for the local community, especially in areas where access is limited during flood or rough terrain conditions. Our solution is a suspension footbridge designed specifically for community use. This type of bridge is ideal because it spans long distances without needing multiple supports in the water. It adapts well to uneven terrain and it minimizes environmental disruption. As shown in our model, the bridge uses towers, suspension cables, and a lightweight deck system to ensure both strength and flexibility. So to make the project practical and achievable, we propose a modular, community-adapted construction approach. This means that using prefabricated components for efficiency, incorporating local materials to reduce cost, and engaging local labor to support the community. This approach ensures that the project is not only buildable but also sustainable. The construction process is divided into key steps, and each step is designed to be efficient, practical, and suitable for rural conditions like Maribago. First is foundation, followed by substructure, superstructure, decking, connection, finishing, and utilities. So let's talk about first the foundation part. Our construction approach here is manual excavation plus small-scale concrete. So this means that we use manual excavation with community labor, apply small-scale reinforced concrete pouring, construct anchor blocks and tower foundation using local aggregates, and minimize heavy equipment use. Next is substructure. Our approach here is cast-in-place plus local materials. So build abutments and anchorage systems using cast-in-place concrete, install anchor rods embedded in concrete for cable connection, use locally sourced materials like sand and gravel, and perform working using labor-intensive method. Next is superstructure. Our approach here is a modular steel plus manual cable installation. We use prefabricated modular steel towers pylons, assemble towers on site using bolting instead of full welding, install main suspension cables manually using rope and pulley system or catwalk, and apply gradual cable tensioning. Next is decking. Our approach here is prefabricated plus timber decking, so install modular steel deck frames or panels, use timber decking local material to reduce cost, assemble deck progressively from one side and add cross bracing for stiffness. Next is connections. Our approach here is bolted systems plus minimal welding. We use bolted and pin connections, which is modular system, limit welding to critical joints only, perform manual tightening and inspection, and ensure proper alignment and load transfer. Next is finishing. Our approach here is paint plus railings plus anti-slip. So install steel handrails and side cable, apply anti-corrosion paint, brush and roller method, add anti-slip treatment on decking and use simple tools for finishing. Lastly, the utilities. Our approach here is solar lighting plus simple systems. So install solar powered lighting, no grid dependency, place basic safety signage, provide natural drainage gaps in deck, and use low maintenance systems. Thus, our proposed suspension footbridge offers a safe, durable, and community centered solution for Madibago. By combining engineering principles with practical construction methods, we ensure that the bridge is not only structurally sound but also accessible and sustainable. We believe this project enhances both mobility and quality of life for the people of Madibago.
I will be presenting the sequence of activities for the construction of our proposed suspension footbridge located in Mandibago, Zamboanga del Norte. The construction follows a systematic process to ensure safety, stability, and efficiency. First is the foundation preparation and installation. The construction starts with clearing and grading the site on both sides of the river. After that, surveying and layout are performed to identify the exact location of the towers and anchor blocks. Excavation is then carried out for the towers, foundations, and cable anchorage. Reinforcement bars and formworks are installed, followed by pouring of concrete, and foundations are then allowed to cure to achieve the required strength. Next is the substructure construction. Base plates and anchor bolts are installed on the cured foundations. The towers, also known as pylons, are then erected on both ends of the bridge. These towers are carefully aligned and secured in a vertical position. After that, cable saddles are installed on top of the tower to support the main cables. The third step is the substructure assembly. The main suspension cables are installed by stretching them across the span of the bridge. These cables are anchored securely on the concrete anchor blocks. Cable tension is then performed to achieve the required sag. Afterward, vertical suspender are installed at proper spacing to support the bridge deck. The fourth step is the deck erection and placement. Stiffening beams and transverse floor beams are installed and connected to the suspender. The bridge deck is then constructed using pressure-treated timber planks. These planks are securely fastened using bolts or screws. Proper alignment and spacing are ensured to provide safe and stable walkway. Next is the structural connections and welding. All bolted connections, include those in the cables, beams, and towers, are tightened. Welding is carried out only where necessary. All joints and connections are inspected to ensure the overall stability of the structure. The sixth step is surface finishing and detailing. Anti-corrosion paint is applied to all steel components. To prevent rusting, the timber deck is treated with a protective sealant, and an anti-slip surface is applied to improve safety. The site is then cleaned and excess materials are removed. Finally, we have utilities integration. Railing and handrails are installed along both sides of the bridge. Safety mesh or netting may also be added if needed. Lighting systems such as solar lights are installed for visibility at night. Safety signage provisions are also included to improve the overall functionality and safety of the bridge. In summary, the construction follows a step-by-step process from foundation up to finishing and utilities. Each activity is carefully carried out to ensure that the bridge is safe, durable, and suitable for community use.
I'll present the work breakdown schedule and project plan for the proposal bridge construction project. Based on the estimation, the total construction duration is approximately 52 days, about 2 months. However, considering the possible delays such as weather conditions, logical issues, and modular construction adjustments, project duration is estimated to 3 to 4 months. The project uses modular lightweight components, meaning some bridge parts are prefabricated off-site. Because of this, the heavy equipment is not required and most activity will rely on manual installation method. For equipment plan, the project will use essential tools only. That includes the concrete mixer for anchor blocks and foundations, a generator set for power supply, a pulley system for a manual cable launching, concrete vibrator for compaction, hand tools for assembly, and wheelbarrow for material transport. The construction work is divided into 7 major phases, which is first, the mobilization, which includes the site, clearing, layout preparation, and delivery of materials lasting about 5 days. Second is foundation work, involving excavation and construction of anchor blocks for 10 days. Third is the tower installation, where prefabricated towers are assembled for 7 days approximately. Fourth is cable installation, performed manually using a pulley system for 10 days. And fifth is the suspender and deck installation, including hanger installation and timber deck placement, taking 12 days. Next is the finishing works such as installing the railing and final adjustment for 5 days. Finally, the project ends with inspection and turnover, which includes the testing and final evaluation for 3 days. In terms for manpower, the project requires one project engineer, one site engineer, skilled workers and equipment operator, carpenters and local laborers. Worker allocates varies depending on each activity to ensure efficiency and safety. Overall, this project emphasizes efficient scheduling, minimal equipment use, and community labor participation, making the construction practical and cost-effective.
Material cost estimate. A. Foundation and anchor blocks. Cement, sand, gravel 400,000 pesos. Reinforcing steel bars 250,000 pesos. Formworks like wood, steel 100,000 pesos. Subtotal will be 750,000 pesos. B. Towers fabricated. Structural steel 800,000 pesos. Bolts, plates, fittings 200,000 pesos. Fabrication and installation 300,000 pesos. Subtotal will be 1,300,000 pesos. Main cables and suspenders, steel cables 900,000 pesos. Cable clamps, hangers 300,000 pesos. Miscellaneous hardware 150,000 pesos. Subtotal will be 1,350,000 pesos. D. Decking system. Deck panels, timber 600,000 pesos. Steel framing 400,000 pesos. Fasteners 100,000 pesos. Subtotal will be 1,100,000 pesos. E. Railings and finishing. Steel railings 250,000 pesos. Paints and anti-slip coating 150,000 pesos. Subtotal will be 400,000 pesos. Total material cost will be 4,900,000 pesos. Labor cost estimate, project engineer 120,000 pesos, site foreman 80,000 pesos, skilled workers 384,000 pesos, laborers 360,000 pesos, carpenters 150,000 pesos. Total labor cost will be 1,094,000 pesos. Summary of total cost. For the total materials, cost is 4,900,000 pesos. Total labor cost will be 1,094,000 pesos. Grand total will be 5,994,000 pesos.
Every step is a story, and every climb is a fight, and every child is determined to reach that light. This bridge will carry them where future awaits. A safe path to learn, a chance to grow, a future they deserve, and a life they know. Invest in Apex because this is more than just a project. It's hope, it's dreams, and it's a place they called